Maybe the host for this, so you are having a powers of recording. So I request that you can record the, but we'll start the recording of this and then you send me the copy of that. Is
Yes,
it
sir.
okay?
Yes, sir. I've started it.
Okay. So yesterday we started with resonant DC link inverter, and main purpose is we want to reduce the switching losses in the bridge inverter, a two-level bridge inverter, and for that we make the DC link to oscillate, and that we have seen it here. How should be our DC link voltage? DC link voltage should oscillate. Average voltage of that will be a V, but it oscillate at a 0 to twice V, and whatever turn on and turn off of the switches in the bridge, we have to done at a 0 voltage, so the switching loss in the inverter will be reduced. And to generate the oscillations in the DC link, we have to use one separate switch. We have shown it here. By closing this switch for a very short duration, when voltage across capacitor reaches 0, you close this switch for some time and then open it, and then we start the oscillations. And in case of this bridge inverter, we don't require this switch, external switch. Instead of that, one leg devices S1 and S4 can be made on simultaneously, so that the purpose of this switch can be done. So it is possible you can go for any two devices from other leg also, you can switch on and do the purpose. And we have seen it here. We generate the oscillating DC link, and we can operate the inverter as a resonant DC link inverter. So here we have shown the practical circuit where LR and CR are the resonating components, and voltage across the CR, that is a DC link voltage, it oscillates two times of the VD normally. But if you want to reduce the voltage rating of the device, we have to clamp this voltage to a 1.5 times of the VD. There are passive circuits are there, but we are not discussing more detail about the passive circuit, and we can discuss one active circuit, that is a clamping of DC link to a 1.5 times of VD, and that is active clamping. We have discussed yesterday. So in case of active clamping, we require additional two components. One will be a capacitor and other will be IGBT with anti-parallel diode, and these two components will be connected in series across the inductor. And then yesterday we discussed the operation of this, particularly how the active voltage clamping works. And for that, we have shown it here. This is the one leg, we have shown it here. So initially we turn on both Q1 and Q4, or T1 and T4, or S1 and S4 we can turn on. And we have shown that the current will have a increasing tendency because of we are shorting the DC link, and this inductor will come across the DC link. Inductor will come across the DC link, and current through the inductor will start increasing. A rate of change of current of the inductor will be increasing for this red current, particularly we have shown it here. And because of that, whatever polarities of inductor we have shown it here, particularly left hand will become plus, it opposes the change. So this will be a plus, and then this will the minus voltage polarity. And once you turn it off, very short duration we are turning on. Once current increases, then our voltage across this current will pass through the, when you turn it off, this current has a this path, current will pass through the capacitor, and voltage across capacitor increases. And whenever voltage across capacitor increases 1.5 times VD, whereas this is the VD, this voltage is the VD, and capacitor, let us assume, charge to 0.5 VD. So total voltage across these two capacitors which are connected in series will be equal to 1.5 VD. And when capacitor voltage exceeds 1.5 VD, our diode deconducts, and the path of current we have shown with a blue color. When your diode conducts and the voltage is across it will be clamped to a 1.5. And whenever our current has a tendency to decrease, so here voltage across the polarity, voltage across the inductor polarity will be the here shown it here with a blue that this terminal will become now positive, right side and left side will become negative, and it will force the current through this. And whenever that turns on, at the same time we turn on the Q1, and when current this inductor current reaches to a peak and then tries to reverse, then we are having our Q1 will be path for the reverse, and when the current energy stored becomes zero, the Q will be turned off. So this is the operation of the circuit. Now our interest is we have to go for how to control this inverter. A conventional BSI, we are having various methods. Conventional BSI, we are having a various methods of controlling the two-level inverter. We are having a 120 degrees mode, 180 degrees of mode, sinusoidal PWM, then space vector PWM, hysteresis current control PWM. So many techniques are available for voltage source PWM inverter. Whereas in case of our resonant link inverters, we are having one technique we are discussing, and that technique is sigma delta modulation or sigma delta technique. We are showing it here. Now in case of this is our DC link voltage, resonant DC link voltage, the voltage may be 1.5 VD. Okay, so this voltage is 1.5 VD. We have clamped it to 1.5 times of the VD. And whatever switching we have to do, the switching we have to do at 0 voltage. We have to do the switching. And now we want a AC voltage. How to fabricate the AC voltage? So we are taking it a positive, okay, one complete pulse, integral pulse we have to take it here. And we have shown it here. If you want to increase the voltage, we have taken the positive here. We want to reduce it, we go to the negative like this. So here, whatever switching we have to do of the switches, that will be done at this. So this will be how we are fabricating the output voltage by picking a complete DC voltage pulse, you can call it. We have to pick a complete DC voltage pulse. This pulse we have pick up as it is, so it is positive we pick up. We pick up this positive pulse as it is. Then here we invert this, we take a negative side, this pulse at the negative side. Then next three we are taking it as a positive here, this at the positive, we taken this. Again next two we are taking in the inverted fashion. So these two we are taken in inverted fashion, and so on. And so the here our output voltage will build up like this by picking a entire pulse, whether it will be appear as a positive or the negative depending upon the requirement. So this will be how the DC link voltage, that DC link is the resonating DC link. It is varying its magnitude from 0 to 1.5 VD, and by picking a complete pulse, whether it will be appear as a positive or negative at the output of the inverter, and based on the switching we can get whether it is a positive or negative, and based on that we'll get the output voltage waveform. Whereas in case of our conventional BSI, our DC link voltage is a constant and ripple free. A red waveform, that will be our DC link voltage, which is a constant and ripple free, and we are using the PWM technique here. Okay, and with the help of that PWM technique we are getting the output voltage. Here we have shown one cycle of the output voltage. Here we have shown just the half cycle. Remaining half cycle we can complete. Here one half cycle output we have shown. Remaining half cycle, negative half cycle we can complete. So that will be clearly showing how is the voltage waveform difference In case of a voltage source inverter, constant DC link voltage, and what should be the output voltage waveform in case of a resonating DC link inverter. So is it clear what is the difference we are getting? And this PWM technique, which we have to select whatever this pulse at DC pulse that should be appear as a positive or negative, we have to select based on the switching of the device. And how is our sigma delta modulation technique? For that, let us consider this diagram. Here our input is a DC link. Here it is shown as the AC. It is also possible with a high frequency AC, but we can call it will be a DC link here. So we can correct here what should be our waveform here. It will be just we have shown. A waveform will be we are having just the pulses. Whatever this will be a DC link voltage, a resonating DC link voltage we are having, and what we are is the whatever the switches we have control at the zero voltage. So this is the input to the. So here you correct this. It is not the high frequency AC. It is a resonating DC. It is available at the input to the inverter. So this will be our inverter. We have shown it here, and DC input to this is the resonating uh, DC link voltage. And now here we are taking it a feedback. So this is a one particular configuration we have shown for one leg. So control circuit will be a we are having a three legs. So this is a control circuit. We have taken a feedback from A phase. So whatever our reference voltage VAO star, that will be our reference voltage. Is the reference voltage we are having, and that is our sinusoidal reference voltage. Then of the same phase we are taking a feedback voltage, that is VAO. So VAO star, that is our reference voltage. VAO star is the reference voltage. This reference voltage is the sinusoidal, and it may be of the output frequency. If output frequency required 50 Hz, this VAO will be a sinusoidal with 50 Hz. With a amplitude, if required 30 Hz, it may be of the 30 Hz with this amplitude. So VAO star will be the reference voltage, and feedback voltage we are taking VAO. Okay, and now we are getting the error. We are integrating the reference voltage as well as we are integrating the output voltage, and difference between these two integrations will be generated as the error. And this error can be a positive or a negative. This error, depending upon integration continuously we are getting the error. The error may be a positive or the error may be a negative. So we after integration will get the error. If error is positive, so we have to switch on upper device. If the error is negative, we can switch on the lower device. Our switching strategy will be based on the error. If error is positive, let us assume that we are switching on the upper device. Or if the error is negative, we are switching on the upper device. If error is positive, we are switching on the lower device. So depending upon that, which is the requirement logic we can implement. So depending upon error, either upper or the lower device can be made on. So here, so this is our what we are having here. So we have shown with graphically here. Let us assume that this will be our VAO star, that is the reference. And if we integrate, that will be our integration of this thick line will be the integration of smooth line what we are having, that is the integration of VAO star dt, that will be integration of this. Whereas if you see it here, a sawtooth type appearing on that will be integration of VAO dt, that will be output voltage. And comparing these two, we are generating the error. And based on the error, whether we have to pick up a output at output side, we have to give a positive pulse or the negative pulse. Let us assume that here S1 is closed, we get a positive pulse at the output, and whenever S2 is closed, we get the negative pulse at the output. So here VAO, let us assume that this will be our VAO, that is the voltage one leg. This is our VAO. Already we have done this, and let us assume that S1 is on. Then our output will be a positive pulse. Okay, it will be waveform like this. In case of VAO, S1 is on, we'll get this, and whenever a VAO, when S2 is on, when S2 is on, whenever this S2 is on, our whatever the VAO will be the negative side pulse, will get it. And based on the error, based on this error function, based on this error, we can switch on either S1 or S2 and we'll get the output of this form, whatever we discussed, and then we'll get the output voltage. That output voltage is let us call as a VAO waveform. This is one leg we have shown. So this particular controller we should require it will be for three controllers. One leg will be controlled by one controller. Okay, so we require three controllers, and for each leg we find out the error, whether error is positive or negative, and based on the error whether we have to switch on upper device or the lower device. If you want to have a error is suppose positive, error is positive means what is meaning? Our output voltage is less. Error is positive means our output voltage is less, and when error is positive we want to increase the output voltage, so we have to switch on the upper device. So when the error is positive, so we can add it here. When the error is positive, so this is for positive E, you can call it. So S1 should be on for positive E. Whenever our positive E is there, whenever positive E is there, error is positive, then we switch out the S1 and our output voltage will appear as the positive pulse. When the error is negative, it means that when error is negative, when error is negative, it means that our actual voltage is higher. So we want to reduce it, and for reducing this, we want to turn on the lower switch. So we turn on the lower switch. So whenever error is negative, we switch on the lower switch, and output will be appear as the negative side. So the average integration will go on decreasing this. So in this fashion, we can obtain the output voltage. So this is one technique we are using for a resonant inverters, DC to AC resonant link inverters. This is one we have shown what will the waveform of sigma delta modulation, and this is what waveform of sinusoidal PWM, which we are using in case of voltage source inverter, where our DC link voltage is fixed. Here our DC link voltage is the resonating. We use a sigma delta modulation technique. Here we have shown the closed loop control for one leg. Similar other two controls will be, so each leg we are controlling independently. Okay, that is the meaning of this. And entire pulse, DC pulse, entire DC pulse, whether it will be appearing as a positive or negative depending based on the error generated by the system. So this is all about our this sigma delta modulation technique. Any queries? Any doubt?
No, sir.
Okay, so this will our complete our third module. We are coming to end of the third module, and what will be a conclusion of this particular module? So we have to use a high frequency switching for the converters, and we want to use a high switching frequency for the converters in general to reduce the size of passive components so that our power density will improve. But at the same time, when we are operating at a high switching frequency, switching losses will increase. And our interest is we want to reduce the switching losses. And for that, a soft switching is desirable. We should go for soft switching, various soft switching techniques we have discussed, and we can go for a zero voltage switching or the zero current switching, and based on that we can reduce the losses, and as the losses are reduced, our conversion efficiency will improve, and our di by dt and dv by dt also in case of soft switching will be less. As dv by dt and di by dt are less, definitely the problem of electromagnetic interference EMI will also reduce, and in all we get a equipment, compact equipment with a better efficiency and better power density. So this is what one particular we can have. Some applications we are using this resonant converters. One of the application we have shown that will be induction heating, small capacity induction heating, as well as the DC to DC converters also we can use when we want to operate at a high switching frequency. So this will complete our third module. Any questions?
No, sir.
Now let us start with our fourth module, and our fourth module is we are going for. Is it screen is visible?
Yes, sir.
Our fourth module is a photovoltaic inverter. Okay, we are in the fourth module. That will be we require some specific inverter configurations when we are operating, whenever we are using the solar power generation. When we are using a solar power generation, we are required some specific requirements of the inverter. They are having very specific inverters for solar power generation, and our intention is we are going for major only on single phase configurations. We are going for a rooftop solar power plants, a small capacity, maybe 2 kilowatt, 5 kilowatt. In that case, we require a single phase inverter topologies, and our more trace will be whatever existing technique, whatever the full bridge inverter, what are the drawbacks associated with it, and how it can be eliminated with the uh, uh, topologies that are available in the market. So now we are having two types of solar power plants. One is grid tied or grid connected, and other is the standalone. We are having two types. I think you are having one special subjects on that. We are not going more with that. Okay, so we are having the two types of the solar power systems. One is a standalone, where we require the batteries to store the energy, and we have seen that main is the maintenance and the life of the battery, maintenance cost and the life of the battery. And to overcome this, very one of the best option is a grid integrated solar systems or grid connected solar power plants. And now the trend is almost 90%, more than 90% whatever installed plants, they will be of the grid connected solar power plants. Our college is having also a grid connected solar power plant of 125 kilowatt peak. You can have a time, you can visit, it will be on the top of the main building. Now we are going for the classification of inverters based on the capacity. So whenever we are having a small inverters rating of inverter is just 50 watt to 400 watt. Capacity is very low, maybe a 50 watt to 400 watt. These inverters we can call as module integrated inverters. These we can call as the module integrated inverters. When a capacity is from zero point 0.4 kilowatt or 400 watt to 2000 watt, that will be we are going for a rooftop small. We are having a in our house top we can use a solar power plant maybe of 2 kilowatt, and that particular inverter is named as the string inverters. Then another we are having whenever capacity, some commercial installation may be required. Okay, a multi-string inverters that will be 1.5 kilowatt to 6 kilowatt. Mini central inverters, this three-phase configuration. This may be also a 6 kilowatt, maybe a three-phase configuration. So we are having a mini central inverters. Just the rating is 6 kilowatt to 100 kilowatt. And central inverters that may be a 100 kilowatt to a 1 megawatt. That may be the range of this. So this is the what we are having. Just the inverter classification. So one is a module integrated inverter, other is string inverter, then multi-string, mini central inverter, and the central inverters. Just they are classified based on the rating, power rating of the inverter. Now, if you look at the history, so first solar power plant that may be installed in 1980. Okay, so first grid tied, grid connected solar power plant is installed in 1980, and in that case, we use that time 1980. We don't have a MOSFETs, IGBT, GTOs. Okay, and that time what we are available was a thyristor. So this will be a thyristorized solar power plant installed in 1980. After thyristors, then power transistors will come in the market. Okay, and power transistor based plant, that is SMS company, they are installed in 1990. And after that, the new devices come IGBT and MOSFET. And nowadays, particularly all these from the string inverters 2 kilowatt or zero point 0.4 kilowatt to this, we are using the IGBT devices, IGBT or maybe IGCT. Okay, what devices we are using is the IGBT. And for a particularly module integrated inverters, this will be low capacity. Particularly we are using the MOSFET. We are using the MOSFETs. So nowadays we are not using either power transistors or the thyristors for the particularly inverter applications. Power transistor is now obsolete device. It is not used at all uh, because it requires a high base current to turn it off. A beta gain, turn off gain is just 5. So if you want to turn off 100 ampere current, we require a 20 ampere base current. So that is the drawback of this power transistor. So nowadays we are not going for power transistors and inverters, particularly power transistors and the thyristors for the PV inverters, and devices which we are using will be the MOSFET and the IGBT. Just this is what we can have. Now if you have a compare, we require inverters also for motor drives, induction motor drives. Then what will be the difference between these two? So here if you see the diagram of this, just we have shown it here, a block diagram that will be grid tied PV system, grid connected PV system. So this is a PV solar array. So we are having a solar modules, then solar array, and then this is our PV panel, which will give a DC voltage at this. Then we require a capacitor like this, and then after that we require the DC to DC converter. A solar voltage may be a lower voltage, that may be solar panel available voltage may be lower, where inverter input required voltage may be higher. So we require a step up of the voltage. So we require a step up of voltage, as well as this DC to DC converter. Everybody knows we want to operate the solar power solar panel at MPPT. So we are using the this particularly DC to DC converter. What is the job of this? Okay, it will be step up. We maintain the DC voltage here, whatever required inverter voltage level. We have to maintain constant. That is one job, and operate the panel at MPPT. So this particularly use of DC to DC converter. This use of DC to DC converter is we are having a main intention is operate the panel at MPPT. MPP. Various techniques we are that operate the panel at MPP. So this is the one of the requirement. Always every solar system we should have always operate at the MPP. Whatever available energy we can extract possible maximum available energy from the PV panel depending upon the solar radiations. Solar radiations may be changing from maybe 100 watts per meter square. Radiation may be from 100 watts per meter square to 1,000 watt per meter square to 1,000 watt. That may be the range depending upon the radiations. So we have to operate as the radiation changes. We have to change the operating point, and this operating point is changed by changing the voltage here. This particular 2 points we can change the voltage, and this voltage is changed with the help of this DC to DC converter. So this DC DC converter changes the voltage operating point of the solar panel so that the solar panel we can extract the maximum power. So that is the one job we require. DC to DC converter, two things: it has to give a constant voltage at the input of the inverter, and another is operate the panel at maximum power point. And then this we are having a voltage source converter, can call it as inverter or voltage source converter, DC to AC. And this we are connected to the grid through a filter. Inductances are required. Through the filter inductance we can give the power to the grid. Here we have seen it here, a voltage source converter, or you can call a PWM inverter and PWM rectifier. Already we studied this. This will be a PWM rectifier and PWM inverter, a PWM converters, and it is possible to supply both powers. Our active power will be from solar panel to the grid, but reactive power flow can be both directions. Reactive power, that Q power, that can be possible to have both. We can supply the reactive power or we can observe the reactive power. That is the beauty of our voltage source converters. So this particular system, it can give a active power to the grid, it can supply the reactive power, it can absorb the reactive power of the grid depending upon the requirement. So this is what now this is what we can call as a grid connected PV system. And now for that, what are the jobs it has to do? And we are saying here one thing: PV inverters are more complex than motor inverter. So for induction motor drives, we are using the inverters. We studied the applications, and these inverters are simple as compared to a PV inverters. Motor inverters, motor drive, induction motor drive inverters are simpler as compared to PV inverters. And what are the reasons for that? And these are listed why they are more complex. We have seen it, they have to need to boost the voltage. One thing is we have to need to boost the voltage. So we require DC to DC boost converter. Then we require a grid connection filter. We require filter at the line side or grid side. Then when grid is failed, when grid supply is off, here we require a grid disconnection relay. In between that, let us assume that we require a grid disconnection relay. So when the supply fails, our PV system should be disconnected from the grid. That is the another that is a grid disconnection relay. At the PV side, we require a DC switch. Here at this DC switch is required at the PV side. At the PV side, we require the DC switch here. So DC switch is here. This is DC supply. We require DC switch at the DC side, and grid disconnection relay. When grid fails or grid is off because of some maintenance problem or faults, immediately our PV system should be disconnected from the grid, and for that we require a relay. We require grid disconnection relay. DC switch is required at this at the DC site. And also what important is, we have discussed one thing, our panel should operate at a MPPT. So we expect the possible maximum power. We extract the possible maximum power from the solar panel. This is islanding. Is our solar system should become separate when grid fails. That is anti-islanding techniques we have to use. Then we have to require a grid synchronization. When power resumes, when power resumes, automatically our panel, our solar system should be connected to the grid. That is, and for that we require a grid synchronization system. Solar panel, solar system should connect automatically to the grid when power resumes. That is our grid synchronization. Similarly, we have to send data to a central utility central. What is the power, voltage, current, and for that we require a data logger of this. And so here, particularly, so these are the functions required to be performed by the solar power system, solar inverters, and so that our PV inverters or solar inverters are more complex than the induction motor tri inverters. We have to step up the voltage. Then we require filter at the grid side. LCL filter normally we use. Then we require a grid disconnection relay. When grid fails, we have to disconnect it. That we can call as islanding. We require a DC switch is we require a DC side. Then grid synchronization, we have to reconnect the solar plant when power resumes. At the same time, power generation data, voltage, current, all this data is to be stored and available online, and for that we require data logger system. And now whatever inverters, our particularly scope is, we are going for a single phase inverters. Whereas here we are having a, sometimes we are using the, here we have not shown the isolation. Sometimes grid and PV system isolated with a transformer, and that we can call as a galvanic isolation. But if you use a transformer in between the PV system and grid just for isolation purpose, then definitely overall efficiency will be decreased by 1 to 2%. Transformer efficiency is almost 5%. So overall efficiency of the system, a transformer efficiency may be 95-96%, but overall efficiency of the system will be reduced by 1 to 2%. So we want to connect the inverter directly to the grid. We don't require the isolation, galvanic isolation between the PV system and the grid. Now we see the construction of PV panel. A PV panel consisting of semiconductor, glass, then a grounded metallic frame. And so that, and this is rest on the ground, so which creates a capacitance between panel and ground. So this will be a one capacitance that will be always associated with the PV panel. That capacitance is the panel to the ground capacitance, and this value will be just 10 nanofarad per kilowatt rating of the panel. Okay, so that will be, and because of that particular panel to ground capacitance, we are having a leakage current and DC injection currents are present, and that should be less. If you consider the life of PV panel, so presently manufacturers stating the life of the PV panel is almost 20 years. So once you install the PV panels, that life of the PV panels is the 20 years. Whereas our life of inverters is approximately 5 to 7 years. Okay, the research is going on the inverter, how to increase the life to the higher values. At present, we are having bottleneck is the filter capacitance, which we are using at the input of the inverter. The life of that may be 5 to 7 years. So we say that the life of inverter is approximately 5 to 7 years. And now we want to avoid the transformer. So intention to avoid the transformer uh, is to improve the efficiency and the cost of the system. So one is whatever our grid connected PV inverters. In that particular grid connected PV inverters, we are not using the transformer for isolation, power transformer for isolation between the PV system and the grid. Sole purpose is want to reduce the cost and improve the efficiency. And here we have just shown us which are the, you just go through the particularly the manufacturers of the grid connected PV inverters, and we are having SMA, various companies, multinational companies, SMA, Sunways, Conergy, then Ingetim, Danfoss Solar, Refu. So many companies are there. So we have listed here 5-6 companies. You can find out. So many companies are in the market for manufacturing the PV inverters, solar PV inverters. And normally the efficiency range of this particular solar PV inverters, they are having a stating the range may be around 97 to 98. It is not the overall conversion efficiency. It will be just the solar inverter efficiency. Inverter efficiencies, inverters we are operating almost efficiency as 97 to 98%. Okay, that will be values given by the manufacturers of these particular inverters. So here we are having, these are the companies particularly which will be manufacturing these SMA, Sunways, Conergy, Ingetim, Danfoss Solar, and Refu. These are the companies, multinational companies. You can just go through the Google and find out the more data on this. Now let us go for our interest is a more our particular this module is we are going for a single phase full bridge inverter. We are going for a single phase full bridge inverter, various topologies. Now here one thing I want to trace here, whatever this full bridge inverter, whatever we are using for drive applications, single phase, and they are not, this inverter is not suitable for solar inverter as a PV inverter. Whatever this bridge inverter, is it this visible? Slide is visible?
Yes, sir.
Yes. So now we are finding out various other topologies of the single phase inverter suitable for PV applications. Our motivation is we have to find out what are the other topologies of the single phase inverters suitable for PV applications. First, at this instant, I can say this will be our H bridge. Is it right? A single phase full bridge we can call as H bridge, and this H bridge also we have seen H bridge, a cascaded H bridge multi-level inverter where basic unit is the H bridge. This particularly H bridge, or we can another name for the H bridge is a full bridge, single phase full bridge inverter. This inverter is not suitable for application as the PV inverter. Applications as a PV inverter, we are going to discuss in due lectures about this. why it is not suitable for as a PV inverter. Now this is our, we represent a PV panel. This will be a PV panel. We have shown it here. A PV panel is normally working as a current source. Okay, and then we are putting it a large capacitor. So here our voltage source it will become. And this dotted you have seen that will be a leakage. This will be a capacitance between the solar panel and the ground. This will be a capacitance between the solar panel and the ground. That capacitance and voltage across it, that we can call as VPE. VPE, that will be a voltage across this leakage capacitance, that VPE. And whatever the voltage of the solar panel, we can call as a VPV. We use a capacitor across the panel, that is a CPV. And then we use the four devices. Here use the convention, normally we are calling as S1, and then we are having a S2, S3 and S4. Here names are given, we are sticking to the book. I will provide the soft copy of this particular chapter. So as per their convention, one leg is having marked devices S1 and S2. Okay, earlier case we are using our, in first leg our device named we are calling as a S1 and S4. Any convention we can use, but here they are used as a first leg, they are having S1 and S2. Our case we are calling it as a S1 and S4. Second leg we are having S3 and S2, here S3 and S4. Okay, we particularly for this we can stick to this. Okay, so this will be our devices, will be a IGBT, particularly with anti-parallel diode, four devices. One leg we are having devices S1 and S2. Other leg we are having devices named as S3 and S4. So DC input we are giving, and AC output is connected to a grid. We have to connect the grid through a grid inductor, you can call it a filter or filter inductance, which will be required to connect our inverter, single phase inverter, to a grid. And grid is, we are having single phase line in neutral, and our neutral is grounded. So this is the configuration. And now we have seen that, we'll just discuss, already we have discussed, we briefly, very hurriedly go through the various control techniques of this single phase bridge inverter. So modulation strategies you can call it, or the PWM techniques you can call it, for a single phase full bridge inverter. And there are three modulation strategies. Three modulation strategies for one is bipolar switching, unipolar switching, and the hybrid. Have you studied what is mean by the bipolar switching? Have you studied what is mean by the bipolar? Are you knowing what about what is mean by the bipolar switching? Anybody? Have you studied? Okay. What is mean by the bipolar switching? I will just go through this. This is our, what waveform we have shown is the bipolar modulation. Here our output voltage will be either plus VD or minus VD. Okay, here output voltage will be either plus VD or minus VD. And here what we can say, in this case, these devices will be operated simultaneously. So S1, S4, these cross devices, S1 and S4, they will become on or off simultaneously. Similarly, the devices, these devices S3 and S2, they will become on or off simultaneously. When this is on, these two are off. When they are on, these two are off. So they will be working, okay, S1 and S4, they are working simultaneously. So when S1 and S4 they are working simultaneously, output voltage, let us assume it will be a positive. So this will be a positive, we just represent. This will be a positive whatever VDC. When S1 and S2 are, S1 and S4 are on, whatever marked with red color, S1 and S4, they are on our, so this positive terminal of the output is connected at the upper terminal, this positive, and negative will be connected to this. So output voltage will be a positive VD, we can call it, when S1 and S4 are on. And whenever S3 and S2 are on, we have seen that when S3 is on, this will become positive, lower terminal will become positive, and upper terminal will become negative. So that will be, so only two voltage levels are available. Only two voltage levels are available, plus VD and minus VD, or plus VDC and minus VDC. Zero voltage is not available. That is the strategies what we can call it as a bipolar switching. This particular strategy is S1 and S4. S1 and S4 are operating simultaneously, becoming on and off with PWM simultaneously. S3 and S2 will be operating this. So we require, how to obtain this? One carrier wave we compare with the one modulating wave. Okay, we compare a carrier wave with a modulating wave. So here you say this will be a positive whenever this is a S1 and S4, we can turn on it here, and S2 and S3 when we want a negative. So for this, our control signal, we are having a one carrier wave. We compare with a modulating wave and generate the switching signal for four devices. So this two signal comparison, carrier wave and modulating wave comparison, will give the four switching signals for this. And based on that, our output voltage levels, we don't have a zero voltage level. Our output voltage will be either plus VD or the minus VD. That is our one fundamental component is this. That technique we can call as the bipolar technique. Okay, bipolar modulation. And how this bipolar modulation, let us our positive current. So here, in this case, whenever we are connecting this particular solar inverter to the grid, it will be just like a working as a current. So it is just feeding the current to the grid. It just feeding the current to the grid. Now let us consider our devices. A positive current, output positive current means the current will be in this direction. That current you can call in the grid left to right. That correct current we can call as a positive current. And here positive current, and let us our switch S1 and S4 are on, and we have shown the path for the current. We are already shown the path for the current. This will be a path. Okay, whatever dotted path, switch S1 is on. Through this it will go to the grid through a filter inductances, then through S4 it will be coming back, and this will complete this. So here our output voltage, we can have a positive voltage here. This will be a positive, and the current is a positive. Now here one thing is there, suppose one of the device is off, then we can have a freewheeling operation. One of the device is off, our freewheeling operation. Let us assume that S1 and S4 are here. Okay, this will be the one case. And whenever both are off, let us assume that these devices are off. And then how the current path will be there, the path of current. Let us assume that both S1 and S4 are off and current is positive. and current is positive. This current is positive, but how it finds the path? Okay, how it finds the path? Okay, the current will be a positive. Okay, so I am tracing this with a blue color. It will come it here, and current is positive. Okay, and this current will now go through a D3. Okay, I am showing the path, go through the D3 and then through the capacitor. Okay, capacitor is exchanging power. Path is completed through capacitance to this, and then completes this. Okay, we are having a positive current. When the switches are on, how the current will take place, how the current will flow, that we represented with the rate. How the current will flow when the switches S1 and S4 are on, how the current will flow, that we shown with the red color. But when the switches S1 and S4 are off, but current is still there in the system, then how is the path? Path will be shown with a blue color, the positive current. It goes through the freewheeling diodes and this. What is meaning of this? This particularly configuration exchange the reactive power. Is it right? This exchange the reactive power. So it will exchange the reactive power between which two components are exchanging the reactive power here. If you
L
see
and
here,
C.
L and C are the exchanging reactive powers, and that will affect the power factor of the system, or you can call it. So this will be a drawback of this particular system. They will exchange the powers. Okay. So remaining part of this, okay, bipolar modulation. Once again, we can discuss. So we'll meet on 12th of October. 11th, we are having a practical. I will send you the PDF file of that practical. That will be our, which, how many number of practicals we have completed? Maybe 7th practical we have to complete. I sincerely request you take some time, though you are having your future plans and career and other things. You just take some time to complete the MATLAB simulation. We have completed 6 experiments. I repeated all the people from Sangli region to come and meet, but they are so busy that they don't have a time to visit the college. That is the real situation. Okay, whatever the matter it may be, I request you have to complete the practicals and submit your, okay, upload your PDF files by we have deadline given 6th experiment you have to complete and upload by 13th of this. And our test or lab assessment 2 is based on the whatever term work you have completed and the oral. We are planning for the oral after the a particular our T2. Okay, so that, and based on the oral, we will give the 30 marks for this particular LA2 assessment. So we'll meet on Monday at 1:15 or 1:30 p.m. Okay, thank you.